The operation of all types of electric machines is based on the creation of a magnetic field within which current-carrying conductors are located. In DC machines, the stator creates the magnetic field, and the rotor houses the current conductors. In a basic DC machine, the stator has two poles, while the rotor has only one winding. The ends of the rotor winding are connected to the commutator. When the rotor shaft rotates, driven by a motor, a DC voltage is generated in the armature winding, as shown on the oscilloscope. The basic DC machine is converted to AC by connecting the ends of a second armature winding to two rings instead of the commutator. By rotating the rotor shaft, an AC voltage is generated in the armature winding. The oscilloscope displays the induced voltage in the armature winding, and also a pulse that defines the position of the rotor. When the pulse is high, the AC armature winding is in the middle of the stator poles. The pulses are obtained by fitting a disc with a notch on the rotor shaft and using the electronic circuit shown. However, the design of DC machines is not efficient. Thus, in AC machines, the roles of the stator and rotor are reversed. The rotor creates the magnetic field, and the windings are placed in the stator. Therefore, a DC voltage is applying to the AC armature winding, creating a rotating magnetic field, so that an AC voltage is generated in the stator winding. The final stage, in obtaining the basic AC machine, is to replace the stator yoke. The stator yoke in a real AC machine has the shape shown in the picture. This particular yoke comes from a car alternator. We placed a three-phase, two-poles winding on the yoke in a star connection. We supported the yoke on a base, created on a 3D printer, and screwed the new stator structure to the available test bench. When the rotor shaft rotates counterclockwise, a three-phase voltage with an ABC sequence is generated. The oscilloscope displays the three voltages, as well as a pulse that defines the position of the rotor. When the pulse is high, the AC armature winding is just below the stator winding, A. Similarly, when the rotor shaft rotates clockwise, a three-phase voltage with a CBA sequence is generated. The oscilloscope again displays the three-phase voltages and the pulse that determines the rotor position. The frequency of the voltages in all cases depends on the rotation speed, while the magnitude of the voltages also depends on the intensity of the magnetic field. In summary, the voltages generated by the individual basic machines are shown in the waveforms, with a rotation speed of 900 revolutions per minute.